process, and it was the first to be commercialized. And stereolithography is a laser-based process that works with the photopolymer resins that react with the laser and cure to form a solid in a very precise way to produce very accurate parts. It is a complex process, but simply put, the photopolymer resin is held in a vat with a movable platform inside, and a laser beam is directed in the XY axis across the surface of the resin according to the 3D data supplied to the machine using a STL file, whereby the resin hardens precisely where the laser hits the surface. Once the layer is completed, the platform within the wet drops down by a fraction in the z-axis, and the subsequent layer is traced out by the laser. This continues until the entire object is completed and the platform can be raised out of the wet for removal. Because of the nature of stereolithography process, it requires support structures for some parts, basically those with overhangs and undercuts. These structures need to be manually removed. In terms of other post-processing steps, many objects 3D printed using stereolithography need to be cleaned and cured. Curing involves subjecting the part to the intense light in an oven-like machine to fully harden the resin, and the stereolithography is generally accepted as being one of the most accurate 3D printing process with excellent surface finish, and the limiting factors that include post-processing steps required and stability of the materials over time, which can become more brittle.
Excuse me,
The
Doctor.
second,
Your screen is not gone to maximize. We are not able to see it. Just maximize it.
is it like that?
Actually, the handouts were also visible, so that's why it is not on maximize. Yeah, now
Now,
it's okay. Yeah,
now it's fully visible. Okay.
yeah, sure. Thank you.
Okay. So the next type is digital light manufacturing. Digital light processing. That is a similar process to stereolithography in the sense that it is a 3D printing process that works with photopolymers. The major difference is the light source. The major difference is the light source, and the DLP uses a more conventional light source, such as an arc lamp with a liquid crystal display panel or a deformable mirror device, which is applied to the entire surface of the weight of photopolymer resin in a single pass, and generally making it faster than stereolithography. So this is the typical setup for digital light processing. So this is the stage, and this is the photopolymer, and this is the light source, and these are the lenses, and this is the motor, and also like stereolithography, digital light processing produces highly accurate parts with excellent resolution, but its similarities also include the same requirement for support structure post curing. And then one advantage of digital light processing over stereolithography is that only a shallow wet of resin is required to facilitate the process, and which generally results in less waste and lower running costs. Now the third type is laser sintering and laser melting. So the difference is between the two is like laser sintering happens below the melting point and laser melting happens above the melting point. And these are the interchangeable term that refers to a laser-based 3D printing process that works with a powder material. The laser is traced across a powder bed of tightly compacted powdered material according to the 3D data fed to the machine in the XY axis, and the laser interacts with the surface of the powder material. It centers or fuses the particle to the each other, forming a solid. As each layer is completed, the powder bed drops incrementally, and a roller smooths the powder over the surface of the bed prior to the next pass of the laser for subsequent layer to be formed and fused with previous layer. The build chamber is completely sealed, as it is necessary to maintain a precise temperature during the process specific to the melting point of the powdered material of the choice. Once finished, the entire powder bed is removed from the machine, and the excess powder can be removed to leave the printed parts. One of the key advantages of this process is that powder bed serves as in in-process support structure for overhangs and undercuts, and therefore complex shapes that could not be manufactured in any other ways are possible with this process. In fact, in IIT Hyderabad, we have G concept laser. So basically, what happens that we put, let's say, we are printing inconel, so we will put the inconel like substrate, and inconel powder is feed, and that there is a roller. So the powder will roll on the substrate like this, and then laser is projected, and actually there is like STL file, so it will be doing the slicing, and then only that particular layer is exposed at those particular points using only laser, and that powder bed will solidify at the points where laser is exposed. So that will be the powder will be melted and solidified. So that one layer of the component is printed. Similar way, further layers will be printed, and actually then further the powder will be rolled, and then layer will be protected. And so actually what happens that this powder feeder, this will raise for this powder to be spread, and the bed will this is the building platform actually on this side. Sorry, we have on the right side. My apologies for this. So this is the building platform. So this will go down, and this powder will go up. So this will spread over here, and then for next layer again it will spread over, and well, because one layer is deposited, so now for the next layer that decrease in the height of the platform will be like by one layer, so that it can deposit the next layer. So this is how it is built, and it can happen in vacuum chamber with the argon as the um, inert atmosphere. So the in fact the quality of samples is very good in SLM. So actually we have like three types of facilities: selective laser melting SLM, like concept laser G, and then direct energy deposition, and then wire arc additive manufacturing. So in case of selective laser melting, we can make only small parts, like small components. And in direct energy deposition, we can make laser metal direct energy deposition, we can make medium sized components. And in the case of wire arc additive manufacturing, we can make huge, large components. So, because of the high temperatures required for laser centering, the cooling times can be considerable. And furthermore, the porosity has been an historical issue with this process. And while there have been significant improvements towards the fully dense parts, Some applications still necessitate infiltration with another material to improve mechanical characteristics. Laser sintering can process plastic and metal materials, although metal sintering does require a much higher powdered laser and higher in process temperatures. Otherwise, what will happen? That powder will not fully melt, and there may be some porosities or lack of fusion defects. Now, parts produced with this process are much stronger than stereolithography or DLP, although generally the surface finish and accuracy is not as good. Now, the next type is fused deposition modeling (FDM) and free-form fabrication. So, 3D printing utilizes the extrusion of thermoplastic material and is easily the most common and recognizable 3D printing process. The most popular name for the process is fused deposition modeling due to its longevity. However, this is a trade name registered by Stratus. Stratus is the name of the company that originally developed it, and Stratus's FDM technology has been around since early 1990s and today in an industrial grade 3D printing process. However, this proliferation of entry-level 3D printers that have emerged since 2009 largely utilize a similar process generally referred to as free-form fabrication, but in a more basic form due to it due to patents still held by Stratus. So actually, when company files a patent, the technology is like cannot be used by other companies or other people for a long time, let's say like 10 years or so, and after that it will be open to public. So these patents were held by Stratus, so the technology could not reach to the larger domain in public. And the earliest wrap machines and all subsequent evolutions, like open source and commercial, employ extrusion methodology. However, following Stratus's patent infringement filing against Athenia, there is a question mark over how the entry level end of the market will develop now, with all of the machines potentially in Stratus's firing line for patent infringements. The process works by melting plastic filament that is deposited by a heat extruder, a layer at a time, onto a build platform according to the 3D data supplied to the printer. Each layer hardens as it is deposited and bonds to the previous layer. Now, Stratasys has developed a range of proprietary industrial grade material for its FDM processes that are suitable for some production applications. At the entry level end of the market, materials are more limited, but the range is growing. The most common materials for entry level uh, FFF, that is free-form fabrication 3D printers, are ABS and PLA. ABS and PLA are the name of the materials, and FDM and FFF process require support structures for any applications with overhanging geometries. For fused deposition modeling, this entails a second water-soluble material which allows support structures to be relatively easily washed away once the print is complete. Alternatively, breakaway support materials are also possible, which can be removed manually, snapping them off the part. Support structures or lack thereof have generally been a limitation of the entry-level FFF 3D printers. However, as the systems have evolved and improved to incorporate dual extrusion heads, it has become less of an issue. In terms of models produced, the FDM process from Stratasys is an accurate and reliable process that is relatively office studio friendly, although extensive post processing can be required. At the entry level, as would be expected, the FFF process produces much less accurate models, but things are constantly improving in terms of additively manufacturing, and the process can be slow for some part geometry, and layer to layer adhesion can be a problem, resulting in parts that are not watertight. And again, the post processing using acetone can resolve these issues. Next type of additive manufacturing is laminated object manufacturing (LOM). So this is the diagram for LOM, and it is a rapid prototyping system developed by Helicis Inc. In it, layers of additive layers of adhesive coated paper, plastic, or metal laminates are successively glued together and cut to shape with a knife or laser cutter, and objects printed with this technique may be additionally modified by machining or drilling after printing. And typical layer resolution for this process is defined by the material feedstock and usually ranges in thickness from 1 to a few sheets of copy paper. Now, the next type of the additive manufacturing is binder jetting. So there are two 3D printing processes that utilize a jetting technique: binder jetting, where the material being jetted is a binder and is selectively spread into a powder bed of the part material to fuse it a layer at a time to create or print the part. As is the case with other powder bed systems, once a layer is completed, the powder bed drops incrementally and a roller or blade smooths the powder over the surface of the bed prior to the next pass of jet heads with the binder for subsequent layer to be formed and fused with the previous layer. Advantages of this process, like with selective laser sintering, include the fact that the need for supports is negated because powder bed itself provides this functionality. Furthermore, a range of different materials can be used, including ceramics and food. A further distinctive advantage of the process is the ability to easily add a full color palette which can be added to the binder. The parts resulting directly from the machine, however, are not as strong as with the sintering process and require post-processing to ensure durability of the component. Now, this is the wire arc additive manufacturing setup in IIT Madras, which I have used. And so we have a, gas metal arc welding setup, and the shielding gas used is argon. And let's say we wanted to print AZ91 alloy sample, so we have AZ91 alloy wire connected to this, and this is the deposition direction, this is the working substrate. So let's say we have taken stainless steel, and this GMW equipment is connected here, and this is also connected to the computer. So here actually the print command is given using like G code and M code, and this is like typical. Here you can see that wire comes from here, and this is connected to a CNC machine. So actually G code and M code are very much applicable, which in mechanical engineers, mechanical students work with, and all of you might have read about G code, M code in manufacturing processes. So basically, like this is the like CNC platform. So we can move in X, Y, Z directions. So this is very useful. So we can produce components using wire arc additive manufacturing. Now this is like RCU unit by Fronius. So Fronius actually holds the patent for this wire additive manufacturing. Uh, in fact, all the names in all the welding labs in India are now renamed as additive manufacturing labs. So in fact, welding was having issues with the sort of like job creation, but now all the welding people are getting jobs in additive manufacturing field. So this is something very very promising for mechanical engineers. So you can see this is like single layer, and you can have a multiple beads kind of structure. You see the layered structure there, and this is like the computer screen showing the G code and G code. Here we can write what we want to print, and we can easily manufacture the components. Obviously, we have to optimize the parameters for having the structural integrity of the sample. Now, because it's very very important for additive manufacturing, so I have one session on G code and M code as well in this. So we will discuss the basic CNC programming, code and M codes that are being used in additive manufacturing. मना कर दिया ऊपर से रेट पे तो मना कर दिया The structure of a CNC program. So CNC programs list instructions to be performed in the order they are written. They read like a book from left to right and top to down, and each sentence in a CNC program is written on a separate line, and that line is called a block. And blocks are arranged in a specific sequence that promotes safety, predictability, and readability. So it is important to adhere to the standard program structure. Now the structure of a CNC program. So G codes, the codes that begin with G are called preparatory words because they prepare the machine for a certain type of function. So here I have listed a few G codes like G00, that means rapid motion, and this is used to position the machine for non-milling moves. So all the CNC codes are actually uh, now getting used in additive manufacturing. Like here we use in direct energy deposition or wire arc additive manufacturing. And G01 means line motion at a specified feed rate, and G02 is clockwise arc. Like if you want to move the like the laser head in clockwise direction, then we will give command G02. And G03 means counterclockwise arc, and G04 means dwell, like dwell time, and G28 is return to the machine home position, and G40 is cutter diameter compensation. So this is like in cutting, not in additive manufacturing, but this is like how even in machining tools these are used. So G41 is cutter diameter compensation. Again, this one is not used for additive manufacturing. G42 is cutter diameter compensation, right? And G43 is two length offset. So here it could be like laser length offset and like laser head sort of offset. And G54 is fixture offset, G55 fixture offset 2, and like these kind of commands are there. And G80 is cancel drill cycle. Like this is also used in drilling. So same can be used in like additive manufacturing. But like these are general terms that are used. Some of them will not be used in additive manufacturing, and G81, G82, these will also not be used. Now M codes. So M code begins with the name M, are called miscellaneous words, and they control the machine auxiliary options like coolant and spindle direction. And only one M code can appear in each block of code. So I'm discussing regarding CNC machines. So please don't say that these are not used in additive manufacturing, because some of it will be used. Some are in general like for machining and drilling and so many other operations in lathe also nowadays these are used. M00 is program stop and press cycle start button to continue. M01 is optional stop. M02 is end of the program. M03 is spindle on clockwise. M04 is spindle on counterclockwise. M05 is spindle is stop. M06 is change tool. M08 is coolant on. M09 coolant off. M30 end program.
Abhishek
Now,
ji बोले।
yes. Now, the structure of a CNC program is the blocks are arranged in the following order. First is program start, and then load tool, and then spindle on or coolant on, and then rapid to position have part. So, like some of these steps will be skipped in additive manufacturing. This will be there. Rapid to position have part and machining operation like here it will be like a additive manufacturing operation. Coolant off, spindle off, move to safe position and end program. The steps listed above represent the simplest type of CNC program where only one tool is used. Here like tool will be replaced by like laser cladding head or sort of wire arc additive manufacturing head and one operation performed. So programs that use multiple tools repeat steps 2 through 9 for each. Now, an example of CNC program to have an idea of how a CNC program looks like. Let's see an example. This example program machines a square contour and and drills a hole. So this is for like machining operation. The same kind of operation is used in additive manufacturing. So we will see it block by block. Like this is like start of the program, and then this is the program number and T102.5 and mill tool description for operator start program. G7. So these are important. G17, G20, G40, G49, G80, G90 to safety block to ensure machine is in safe mode, and the T1 M6 load to 1 and S9200 M3. So this means S9200 is like the spindle speed is 9200 RPM. Same way like we will need to have like RPM or some speed that can be given, and this is on clockwise direction. Then we have M8 coolant on C00 x 0 minus 0.025 y minus 0.275. So this rabbit part this goes to this x and y position, and Z43 Z1 H1. So this is like in Z direction, and Z0.1 rapid to feed plane. So these are the like basic commands that are very important. So these are a few more commands like if it is saying y 2.0 2.025, so it will go to this position and like and this is a like line move. Okay, so these are some commands that are very useful. This is such example. So yes, like this is M9. This is like return to machine home position, and G91, G28, Z0, Z91, Z28, X0, Y0. So X0, Y0 means it is coming to the home position, and G90 again is set to absolute positioning. M30 is like end of reset program to the beginning. So this is like end of the program. So these are the G code and M code that makes most of the contents of CNC program, and the definition of each class of code and the specific meanings of most important codes are covered in the next slides. So these are the G codes that are used. You can have a quick look. I have discussed one example. So these are the G codes. Now, letter address command codes. So the command block controls the machine tool through the use of letter address commands, and some are used more than once, and their meaning changes based on which G code appears in the same block. Codes are either modal, which means they remain in effect until cancelled or changed, or non-modal, which means they are effective only in current block. As you will see, many of the letter addresses are chosen in a logical manner: T for like tool, S for spindle, F for feed rate, etc. So these are the letter address command codes like A, B, C, 4, 5, 6, axis, rotary motion, and rotation about X, Y, Z axis respectively, and the angle is in degrees, and up to 3 decimal places precision. So like G0, A 45.325, and B90. So it means like this is giving an angle to the axis, and B is absolute or incremental position of B axis, same as the description or definition is same as A or B or C, and the D defines the diameter or radial offset used for cutter compensation. So here it could be like the diameter of the laser spot could be there. Then E is the precision feedback rate for threading on lathes. F defines feed rate. G address for preparatory commands, and H defines tool length offset, incremental axis corresponding to C axis. I defines arc size and x-axis for G02 or G03 arc commands. Also, it is used as a parameter within some fixed cycles. And J defines arc size and y-axis for G02 or G03 arc commands. Also, it is used as a parameter within some fixed cycles. K defines arc size and z-axis for Z02 or Z03 arc commands, also used as a parameter within some fixed cycles equal to L address. Now, L is fixed cycle loop count, a specification of what register to edit using G10. M is like miscellaneous function. N is line number in program system parameter number to be changed using G10. O is the program name. So this is used in initiation of the program, like in the start of the program we write O and the program name, and then P serves as parameter address for various G and M codes, and Q peck increment in Kent cycles, and R defines size of the arc, like R means radius, so defines retract height in Kent cycles. S is the speed, either spindle speed or surface speed depending upon the mode. T is tool, and U is incremental axis corresponding to x-axis, typically only lathe group A controls, and also defines dwell time on some machines. V is incremental axis corresponding to y-axis. W is incremental axis corresponding to z-axis. X is absolute or incremental position of x-axis. Y is absolute or incremental position of y-axis, and Z is absolute or incremental position of z-axis. So if we write like Z 2.0, so it goes to Z like two position 2, Z equal to 2. Okay. Now the special character codes. So the following is a list of commonly used special characters So, like percentage sign, it is used for program start or end, and all programs begin and end with percentage on a block by itself. And this code is called tape rewind character, a holdover from the days when programs were loaded using paper tapes. And like these brackets are used for comments, and so comments to the operator must be all caps and enclosed within brackets, and the maximum length of comment is 40 characters. So if you type beyond 40 letters, it will not take, and all characters are capitalized. For example, T02 5 by 8 and mil. So this is written within the brackets, and the oblique sign. So this is for block delete. So this will like delete the line, that block, and the codes after this character are ignored if block delete switch on control is on. Example like oblique MOO. So this will like remove this command. So this is like blocking or deleting it, and then this character is for end of block. So this character is not visible when a CNC program is read in text editor, and but does appear at the end of every block of the code when the program is displayed on the machine control. For example, N8Z 0.750. Now, this is another example. So, explain the following program written for a milling machine like N0500 X10 Y25 Z1 S 1250. So, like this is like a speed. M3 N10 Z01 Z5 F100. F is like feed rate. Okay. N15 Z02 X10 Y25. So this goes to X equal to 10 Y equal to 25. I20 Z0 F125. So if we need to understand this program, you can refer to the G code and M code, and you don't need to remember all these because you can go to the standard codes and you can understand. And, N20Z00 Z100 M5, N25 X20, and N30 N30 M30. So these are the like codes that are used, and we can see like this is how it looks, how it starts. So this is like explanation, and N05 is like tool rapid reverse to Z00 to point P01, and then N10 in feed Z01 to Z2 equal to 5, and N15 and XY planes selected automatically. So Z17 tool reverses clockwise. So this is clockwise and around a full circle. So Z02, and N20 N25 rapid reverse 00 G00 retraction, and N30 is and like end of the program is M30. So this is milling a full circle from outside. Now coming on to the selective laser melting of additive manufacturing. So additive manufacturing is defined as a process of joining materials to make objects from 3D model data like SLS file, and usually layer by layer deposition as opposed to the subtractive manufacturing methodologies. And selective laser melting (SLM) is a popular AM technique based on powder bed fusion, which uses high power laser beam for producing full density parts through layer by layer development. And well, like one of the very good advantage of SLM is that it can produce really dense parts compared to other processing methods like direct energy deposition and wire arc deposition. The quality is very good. Only limitation is the components we can create is like very small in size, or not very small, like you can You can create a small component like 10 centimeter into 10 centimeter into 10 centimeter also, but like beyond that it is going to be difficult. And main benefits of additive manufacturing is it has freedom of design. You can give a CAD/CAM file and you can print it, and it can minimize the waste, and it has ability to manufacture complex structure. I have already given example of the bone skull it can produce, and the fast prototyping. So SLM process with optimized parameter. Generally, typical process parameters are like laser power is like 370 watt and scan speed of 1300 per second, and hatch spacing is 0.19 and layer thickness is 30 micrometers. So this is like layer thickness of one layer, and this is like hatch spacing. So hatch spacing is like you print one line and then the next line, so the distance between the center of these two lines is called hatch spacing. So this also has an important role, and generally it is to the tune of 0.19 millimeters, but it depends on the like what is the laser spot diameter and all of that, and how much overlap we want to create. Like if we want to create the overlap between 30% to 40% of this width of the laser bead. Okay, and this is like scanning speed. We are scanning from here to here, and this is the preceding layer or substrate plate. So why we have said preceding layer is because once we have substrate first layer, and then if we are depositing again, then we say like preceding layer. Now this is a layer material processing equipment in IIT Kharagpur, and this is for laser metal direct energy deposition method. So this is the robotic arm, and we use KUKA robotic programming language for running this. We don't use G code or M code in this, and this is the powder feeder. So we can have like deposition of powder here, and this is the like substrate plate. So and but one good thing in this KUKA robot is that we can also provide angle to the laser beam, and that can affect the reflectivity of the like laser or absorptivity of the laser also. And generally the substrate is sandblasted, and because to remove the reflectivity of the substrate, otherwise the laser will reflect and it may damage the laser head. So this is very very important. You can see that this laser light coming from here. So laser is being deposited. At the same time, powder also comes from here. These are the how to say pipes where the powder is coming. And so in CNC we cannot provide the angle to this axis, but in this KUKA robotic arm, actually we can provide the laser angle also. So in CNC we can only shift X, Y, Z. Here X, Y, Z, and also angle we can provide. So this is actually six-axis, KUKA robotic arm. And I'm sorry for the bad image, but I wanted to show how the KUKA robotic like programming language looks. This is not very much visible. I'm sorry for that, but this is how it looks. I wanted to show you how it looks in KUKA robotic programming language. And so conclusions are additive manufacturing, design simplicity, and process chain digitalization, which contribute to continuous innovation. It can be inferred that fabrication of magnesium alloys by AM methods is itself in its novelty. And the other important conclusions are as follows: like achieving improvements in strength, fatigue, and fracture toughness properties in additively manufactured magnesium alloys is challenging task, and additive manufacturing of magnesium implants is still in its infancy state, and probably due to the physical and chemical properties and the low boiling point, surface tension and density, and high vapor pressure increase chance of metal burning in laser exposure, and high reactivity in oxygen atmosphere also depreciates the forming quality. The dynamic degradation may alter mechanical and biological properties, posing the need for elucidation of different implant geometries on degradation rate by using CAD designing and reverse modeling or mathematical modeling methods. The combination of aforementioned techniques may help in achieving the high resemblance to biological entities and optical performance. Now, it also produces less waste and scraps, so additive manufacturing moves in opposite direction compared to traditional production systems that proceed by subtraction. Unlike techniques such as milling or turning, additive manufacturing adds the material needed to create products as a result, and it produces less waste and cuts the resources waste. And additive manufacturing decreases prototyping times and cost. So, thanks to additive manufacturing, because it creates the prototype of a product in a faster and easier and cheaper manner, and other manufacturing techniques such as milling involves considerable configuration and material cost, and since the cost and time of prototyping are lower, you can produce, test, and make necessary changes without too much trouble. In addition, it provides almost instant proof of improvement made. It promotes business digitalization. Additive manufacturing requires continuous and effective dialogue between devices, machines, and robots, and this is possible only through adequate digitalization of manufacturing activities. Hence, the companies invest more in digital and Internet of Things, an essential requirement in Industry 4.0. Additive manufacturing synthesizes assembly process in a single part, and another benefit of additive manufacturing in Industry 4.0 is the simplification of the production process, and in particular, the assembly of products. Traditional components are complex and require multiple production steps, and this raises both material and labor costs and the time required to create and assemble the different parts. AM, on the other hand, allows you to print the group in a single piece. So these are like main conclusions of additive manufacturing and its use in Industry 4.0. So I would like to thank staffs and colleagues and Department of Mechanical and Aerospace Engineering, IIT Hyderabad, India, and also I would like to thank the additive manufacturing labs at IIT Hyderabad, IIT Kharagpur, and IIT Madras, where I have worked, and I would like to thank friends and colleagues who have supported me immensely. And obviously, I was also very new to this field, but now I have worked in three IITs on additive manufacturing. In IIT Madras, I have worked on additive manufacturing. In IIT Kharagpur, I have worked in direct energy laser deposition, laser deposition process, and in IIT Hyderabad, I am working again on direct energy deposition method, but we also have selective laser SLM machine. So, and finally, I would like to thank my family who has always supported me to pursue my research and teaching career. So thank you very much for attention. I am now open to questions from the audience and of course feedback from the audience. And yes, sometimes it may be a little bit boring for all of you also to absorb so much of information, especially it's like years of knowledge gathered together and put it to 2 hour of session. So I would like to thank the organizers also, and a special thanks to Oriental Institute of Science and Technology and their management and Professor Jitendra Pandey, who has took immense effort in organizing this faculty development program. So thank you very much all. Hello.
Yes, sir. Thank you very much, sir. Now participants is requested to ask any question if they have any query or anything else, please.
Participants ask the question.
Hello. Anyone for the questions?
Hello.
Anyone
Hello.
from Bansal Institute of Research and Technology, Bhopal?
Hello.
Yes, Airwar sir, please ask the question.
Good evening, sir. This is Dr. P. N. Airwa from Bhopal, Madhyanchal University,
Yes.
the mechanical department. It's
Hello,
very
sir.
good. Hello.
Hello, sir. Hello, sir.
Ji, sir. I ask one question. First of all, it's a very wonderful session. Topic additive manufacturing. Hello.
Yes, sir. Thank you. I'm listening. Yes, sir.
सर मैं ये पूछना चाह रहा था कि एडिटिव मैन्युफैक्चरिंग में ऐसे कौन से बेनिफिशियल एडवांटेज है हमारी दैनिक जीवन में कि हम ये बता सकते हैं कि व्हाट आर द एप्लीकेशन यूज इन एडिटिव मैन्युफैक्चरिंग इन डेली आवर नीड्स डेली आवर लाइफ.
Yes, at the moment, like additively manufactured samples are being made only for advanced technology, like for making rocket components or aeroplanes or robotic arms or in advanced engine components or medical industry. It has a lot of applications. So in like if you say day-to-day life. If we come across like all the medical implants, they are being made by additive manufacturing. And let's say if now the polymer 3D printers are very cheap. Like you can buy even for 25,000 rupees one polymer printer. So it can print. Let's say in day-to-day life now things are going to be like something like if you need a toothpaste, you will have a printer in your home and you give a command. And it will print directly toothpaste and it will be same cost as your real toothpaste manufactured by normal traditional way. Let's say you want iPhone case, and it can be printed at your home. So that way we are thinking like the technology is going to be so much advanced that you need any component, it can reach your home also now. So in fact, in defense and aerospace applications, it is unavoidable at the moment to avoid additive manufacturing. But in your question is very much valid, how we can use it for day-to-day products. So at the moment, now you can make any additive manufactured samples. So that is very much possible.
Okay, sir. Okay, okay. Thank you very much, sir.
Thank you.
Anyone else having the question?
Any more questions from
Thank you, sir.
participant side, please?
This is Lakhan Patidar, Dr. Lakhan Patidar.
Yes, sir.
Thank you, sir, for your wonderful session, sir. You talk about medical applications, sir, and some materials would be dissolved in our body. How they dissolve and how they harm our body? It may be harm to our body, no, sir? Or not?
Yeah. Actually, at the moment, in medical industry, we are using titanium implants, Ti6L4V, and it is not dissolving. But the future plan of technology is to develop magnesium implants, and magnesium is actually beneficial for the body. So if it will dissolve in the body, it will not harm. In fact, it is like beneficial. Like we body needs magnesium, and magnesium is quite compatible with the bone, and it's the Young's modulus of magnesium implant is similar to Young's modulus of actual bone. So this is like a very very good implant, and the rate of dissolution of magnesium is actually equal to rate of bone growth, like roughly equal, and we can tailor even that rate of dissolution by additive manufacturing process, by controlling the microstructure, by controlling the cooling rate, and so many factors that will come into it. But at the moment, magnesium implants are being developed, and they are not fully operational, and the technology readiness level is like 2 out of 10. But for but for titanium implants, the technology readiness level is like 9 out of 10. So which is it is being used in medical industry, and in fact I have worked in Oxygen Medical Private Limited, where I have actually seen these implants are being sold to the patients on the recommendation of doctors.
Sir, and how can doctors or manufacturer found the pain of patients? How they
Sorry.
discomfort with this material? How can we find the pain of patients, sir, for their discomfort to particular materials, or
So
how
when
how can we identify, sir?
So when actually bone implant is implanted in the body, actually the company which provided the bone implant, they have to take feedback after like certain period of time how the patient is feeling discomfort, and what is the progress. If it is failing, then actually it will harm the reputation of company, and in fact the government can impose like a complete ban of manufacturing on the manufacturing facility of the company. So this is how it is coordinated between doctor, patient, and the company. So it's very very important that all these, in fact, all this data is actually retained for like certain period of time, and in fact, uh, like all the companies have to apply for like US FDA approval, and if some complaint comes from the patient, then they will not get US FDA approval. For different companies, there is different approvals. Like for US, it is US FDA, but generally, if US FDA is approved, then actually like for all other countries you will get easily, because this is like one of the toughest approval to get in medical implant industry. So did I answer your question? Yeah.
Good evening, Dr.
Yeah,
Abhishek.
sir. Thank you, sir.
Thank you.
Good
Yes,
evening,
yes.
Dr. Abhishek. I'm Girish Kumar Khare, and I'm head of the mechanical department at OIST, who is the organizing body for this FDP. So, on the onset, I thank you for your kind gesture. You have given time for us. So, thank you very much for from the organizing committee also. I thank you from their behalf. Then, secondly, for Dr. Lakhan, what I could guess from your question, you were asking whether how we can make a judgment whether a person is particularly intolerant to some sort of material or what, or say I'm not, say I'm having allergic to say silicon sort of material. So then how to measure this? Was this your question?
Sir, my question is to be how can other person find the pain of
Implant.
patient, sir? How can we find the discomfort of patient, sir? Yes, sir.
Yeah.
During after implant, sir.
Yeah. So what I can add on to this with my experience is like for your intolerance to a particular implant material, I can comment on that. Like अगर आपको किसी एक particular implant के material से allergy है या आपकी body इसको react नहीं कर रही है, so normally in US and UK they test the tolerancy of that material with your body. आपको जिसका implant लगने वाला होता है, so they inject some sort of material into your body for some period of time. So they check for tolerancy of that particular implant material with your body. Then if no adverse reaction is observed, then only that implant is going to be into your body. So for that particular material, normally it is done. But about the pain, that is under process, like if the implant is working properly or not, or how the patient is observing some pain or comfortness. So that is underway. I hope somewhat I have connected to that. So, Dr. Abhishek, I have small questions
Sir,
about that.
yes.
Yeah. Like you told me that you were working on magnesium alloys in some aerospace and all that. So you were working with this additive manufacturing for magnesium parts.
Yes.
Yeah. So my question is that this additive manufacturing is taking care of only the part production or the surface treatment also. Like for magnesium, we want to seal the surface. The surface has to be sealed.
So at the moment, actually, as I told you that for magnesium, even the technology readiness level is not too. So this is at the moment in the developmental stage. For example, the additively manufacturing has developed fully for alloys like ALSI 10 mg, Ta6Al4B, and stainless steel, copper, brass, and Inconel 718. But for other alloys, still the technology has to be developed. So I would say that for magnesium we are only in very infancy stage, and we should not comment further for sort of in fact implanting it in regular patients. But this is like future of technology. If we are able to achieve it, then actually it is like very good, because the implant will dissolve and the patient will not have to go resurgery because of bone growth.
So regarding the metallic components, this additive manufacturing is going far towards doing the surface protection also in parallel to the building up the surface, or only it is limited currently to preparation of surface, the metallic parts.
Only at the moment, like preparation of the part, but like some final polishing may be required. But like the surface finish is very good in selective laser
No.
matting.
I'm
Yeah,
not talking about surface finish. I'm
yeah.
asking about the surface protection, like you say For aluminum parts, if you are making aluminum, so we want to do anodizing or like chromatic anodizing, which is getting banned by the REACH convention. So is some sort of improvement into additive manufacturing is going on, which will take care of the surface protection also.
We will have to see what is like application, but like in Oxane Medical Private Limited, I have seen that some implants were getting treated using anodizing, and it also produced a beautiful blue color on the implant because of anodizing process.
Yeah.
So
So, but
it
that
like
anodizing process
provided
is carried out separately, not
that is carried out separately
yeah. So my question
after.
is there any research going on so that the anodizing process or the deposition of aluminum oxide layer on the top of the surface is built printed also?
No, I will have to see, look into like all the research papers for this.
Yeah.
But at the moment, I can only say this one,
Okay.
this thing.
Because if that is done, then it would be a fastest method because you have printed the part, metallic part,
Yes,
then it
yes,
is
yes.
going to the conventional process shops for that chrome acid anodizing or what. So, but if we are able to do the anodizing in parallel to the building up
Hmm.
of part or printing of part, then it will be real
Hmm.
cost saving as well as time saving.
But for example, in additive manufacturing, we have freedom of design also. Like freedom of
Yes.
design is not there in that thing. Like if you want
No,
to, as I
totally.
showed you, yeah.
I'm not asking on that. I was just asking over the further addition on additive manufacturing. So, additive manufacturing, if combined with, say, surface protection part, like in anodizing, what we do, we build up a layer of oxide on the surface of the aluminum part, which protects
Yes,
it
yes,
from the corrosion. Because
yeah,
you told about corrosion, so that's
yes,
why
yes,
I asked this question.
yes, yes.
So,
So
is there any mechanism by which we can infuse that oxide layer on the top of the part which is being finished like that?
maybe like we can have a assembly connected to it. Like
Yeah,
after it is the part
that
is produced
assembly that
using additive. Yeah, that can be integrated. That's where Industry 4.0 can play a role. Where like after it is produced, it can go to the next assembly line, and their
like
anodizing will
like
be
you
done
like you
automatically.
have produced a part of aluminum alloy,
Yeah.
then a powder of some oxide is also fused using the same technology. So then it
No,
will be assembled,
not
not like
using
that.
not using same technology. That will be like next step. So
Yeah,
that can be integrated automatically also. Like as I told that one plant in Philips Turnhout, Belgium, they were having completely automated like robots. The entire plant was run by robots, and only one person in charge was there in the entire plant. So that automation can be implemented. So that's where Industry 4.0 can also play a role.
yes. And for the question of Dr. Premna Nairwar, for the use of additive manufacturing in daily life, I would like to just share one image from the Idea Lab.